All right, quick recap. We're trying to find A in a factored form, PDP inverse. Now, the columns of P are going to be these x's here. And then the diagonal entries of D are going to be these lambdas here. So these are vectors and value real numbers. They have special names. They're called eigenvectors and eigenvalues. Now, we can find an eigenvalue in a systematic way just by thinking about sort of what has to happen here. Before I move on, let's underline that eigenvectors cannot be the zero vector. Eigenvalues can be zero. Okay, it's okay for an eigenvalue to be zero. Okay, moving on. So to find an eigenvalue, let's think about that. Well, we need ax to equal lambda x. So again, we're given a matrix A. We want to find the eigenvalues. Let's think about this equation. Well, let's move things over. We got ax minus lambda x is the zero vector. And we can factor an x off of the right of this expression. So we'll have a minus lambda. We need an I here. We need an I right there. Because if you had, a minus lambda, that doesn't make any sense. That's a matrix minus a real number. Does not make any sense. So a minus lambda, no good. Anyways, so if we're trying to solve this equation, we can think of it like this, and then say, okay, we have a matrix times x, and x is non-zero. So you have a matrix times x and equal to zero vector. So this is a homogeneous system. So we have seen, or you can probably think about this, is that if you have a homogeneous system, like a minus lambda I, and let's say it's 3 by 3, whatever. Okay, the only way this is going to have a non-trivial solution is if a minus lambda I does not have 3 pivots, right? I need there to be a free variable appearing over here. So we'll pose it like this. Okay, so I need a free variable. Another way to put it is to say that determinant of a minus lambda I has to equal 0. Okay, it's an equivalent condition, okay? I only have fewer than 3 pivots here. Another way to say that is that the determinant is 0. Okay, so this equation has a non-trivial solution if the determinant of a minus lambda I is 0. So I will use that to find lambda. Now this is called the characteristic polynomial. Characteristic polynomial of A. And sometimes you write it as C subscript A. The variable is lambda, is determinant of A minus lambda I. Okay, so to find an eigenvalue, we will take this characteristic polynomial and we'll set it equal to 0, and then we'll solve for lambda. Okay, let's see how that works out. In an example, so we'll say find the eigenvalues. of this matrix we saw above, 3, 5, 1, negative 1. Okay, I already gave them to you above. It's going to be 4 and negative 2, I think, but let's find them more systematically. Now, this discussion we just had here says that if I have an eigenvalue, if I have something passing this test, then the determinant of this matrix has to be 0. That's my argument there. So what I'll do is I'll take the determinant of A minus lambda I, and I'll set it equal to 0, and I'll see what happens. Okay, lambda I in this case is the 2 by 2. That looks like that. So my determinant is going to be this minus this. And 5, 1, negative 1 minus lambda. So that's going to be equal to 0. And then when I do this determinant, it'll be a fairly straightforward calculation. 3 minus lambda, negative 1 minus lambda, minus 5 is equal to 0. Now we're going back to, I don't know, secondary something, 2, 3. I work this out. Get minus 3 lambda plus lambda plus lambda squared. Minus 5 is 0. And eventually, I think I'll use quadratic formula or factor if I can. Minus 8 equals 0. I can factor this. Minus 4 lambda plus 2 is 0. So lambda is 4 or lambda is negative 2. These are the eigenvalues. So, in summary, if you want to find the eigenvalues, you take the characteristic polynomial and you set it equal to 0, and you're going to solve. The expansion gives a quadratic, or later on we'll see cubics. We'll have to be a bit careful with the cubics because they can become unpleasant if you have to factor a cubic, but for now that's it. Characteristic polynomial equals 0, solve for lambda. And your answer is here.